Hello again, this is Tim Baldridge for part 2 of Let's Build a JIT, or Write a JIT, I guess the actual title, this will work. So today we're going to talk a little bit about tracing JITs and how tracing JITs work, and we're going to write the tracing part of a tracing JIT. So we're talking about in this series a different type of JIT than what you'd normally experience. In most systems, specifically in languages like on the CLR, we're talking about method JITs. Once we execute a method enough times, or maybe perhaps some versions of the CLR just compile a method the first time they see it. See a method, it's not compiled, compile it in machine code, there we go. The JVM is a little more complex in how it does JITting, and I'm not going to even attempt to say that I know enough about it to say what type of JIT it really is. So I won't go into that. But we're going to talk about tracing JITs. So to my knowledge, there are 3 or 4 main well-known tracing JITs in existence. There was an old version pioneered by, I believe it was HP many years ago. And then we have Psycho for Python, which has since been discontinued because it was too complex and hard to understand. There was TraceMonkey for Mozilla, which I think has also been discontinued because it was too hard to work with and understand. LuaJIT, which actually is still in existence because it is such a simple language to work with in this way that there's no big it's not as big of a problem maintaining the code. And then PyPy. And the PyPy project basically says, yes, tracing JITs are really hard to write, so let's not write it, let's make the computer write it. And that's something we'll get into later in this series. We'll see a little bit of how that's possible. I don't know that we'll actually explore the full ramifications of the PyPy project, but it's pretty cool stuff if you're into JITs. Okay, so a tracing JIT goes about things a little bit differently. And what it says is that when we see an absolute jump, like our interpreter has up here, when we have an absolute jump like this, we're going to keep track of the block that we're coming from and the block that we're going to. And after we see that pattern enough times, that will cue us in that, you know what, I think we're in a loop. So if you look at our code here, this power rec here is a loop. We have these 3 instructions and then we loop up to the top and we go over and over again. So the idea is to detect that sort of thing. And then the next time we jump into the top of the loop, after maybe we've executed the loop 1,000 times or something, then we start tracing. And we're going to kick into a different interpreter that works like the normal interpreter. However, as it executes each operation, it keeps track of each operation in a list and inserts some other guards and information that we'll look at. And then when it gets to the end of that loop, which could consist of many blocks, but when it gets to the end of the loop, it takes that trace, generates code for it, compiles it, and runs it. And then the key part of this is to be able to make certain assumptions about this trace. For instance, if we are using integers like we are here, we may have some polymorphic functions that work with either integers or floats, but we can say, you know what? Nowhere in this trace do we see any mention of floats. So we're going to assume that we are only ever going to be given integers in this code. And we'll put some guards at the top to say if we ever get floats, then bomb out of this JITted trace. But until then, we're going to run this highly optimized code. So the key part of this, obviously, is the tracer. So let's look at the trace. Now, what's interesting is this trace looks almost exactly like the interpreter that we wrote in the last part. In fact, it is the same code. All I really did was copy and paste it and then start adding some data to it. Now, if you go to the old code base, the code base that I've linked on the last video, and I'll link again on this one, you'll notice that I've actually updated the code to use more of a recursive version. So before, we used to have each operation, the last item in each bytecode or operation was a pointer to the next operation. I've kind of cut that out. That was an artifact of working with Prolog, and that I kind of got this code from, and I've been adapting it more and more. So I kind of rewrote the old interpreter. Not much has changed, except for now we have this instruction pointer. And each time we recur in the function, we increment the instruction pointer, and then when we do a absolute jump, we reset it to 0 because we're at the beginning of the next block. I updated as well the partial evaluator to support that, and it works pretty well. And it simplifies the code when we're working in more of a functional code base. So, the trace. We have the current block we're executing. We have the current instruction pointer. We have the current environment. We have the start block, which says this is the block at the start of the loop. If we ever jump back to that block, we need to stop the trace. And then we have the trace data, which is a vector of all the operations that we've executed in this trace. Well, if that's the data we need to keep track of, then this is actually really simple to do. When we have a single argument operation, we recur with the block, increment the IP, the new environment like we had before. The start block hasn't changed, and it never actually will. We just continue to pass that in as data that we need. And then we're going to conj onto trace data, an operation, the bytecode. It's the same bytecode that we executed up here. In fact, we could probably, if I wanted to, even put in like a as inst or something like that. In fact, we have that right up here, don't we? We have it right here, inst. So why don't we just do that? It'll make things a little bit simpler. There we go. So now same thing for this operation. We have op result, the result, the operation arg1 and arg2. Same thing. We're just going to conj onto the trace data, the instruction. Jump is interesting. So if the block we're going to jump to is the starting block, then our trace is done. In which case, we're going to conj onto trace data this operation called loop, which says loop back to the beginning. So if you're executing a block and you see the loop instruction, just jump to the beginning of the block and continue executing again. And then we're going to print out the trace data for debug purposes. And we're going to return this hash map. And this will be picked up, we'll pick this up in the next part of this series. What we're actually going to do with the return value. But we can look at this, the output of this, and it'll be kind of cool to take a look at it. Otherwise, if we're not at the end of the trace, then we just continue. But look at this. We don't actually conj anything onto the trace data. And this is kind of the cool part about tracing JITs, is they remove all branches from the code. All of them. Because this is an unconditional jump, we don't even need to put a guard or anything here. We just inline the next block. So tracing JITs are very, very good at making some assumptions and then inlining a single path of the code. And this works fairly well with code where things could change a lot, but don't. An example of this would be a language like Python or Ruby, where you could change the class information at any time, but you're not likely to. And so we can make certain assumptions and say, we're going to assume that they're never going to change the class of the actual class information. And if they do, well, then we'll throw out all our traces and start over. And they'll have to accept the poorer performance because of the way they decided to write their code. Okay, so if then with an if here. So with an if, we're going to do some other stuff. Well, the idea with the if is to inline the if branch that we took, but provide a guard so we still need to check and make sure that something hasn't changed. But we can still inline some code as well. So we're going to resolve our test value just like before. We're going to figure out what block we're going to be jumping to based upon that. And then we're going to create a guard. So if the operation ended up being true, if our tested value here is true, then we're going to return guard true. Otherwise, we're going to return guard false. Then the block is going to be the other branch of the if that we're not jumping to. And then we're going to emit this instruction called guard type test guard block, and we'll look at what that looks like in a little bit. And then this is pretty much the same with the loop. We have to see, are we jumping? If the branch that we're taking is jumping to the start block, then we're going to execute a loop. Or we're going to put in the loop instruction and continue on. And return the trace. Otherwise, we continue on. Print and stop is the end of the trace. At print and stop, the program is terminated, so there's nothing else to do at all. Now promote. This is the key thing that is added to these traces that makes them really awesome. Promote says, it's saying to the tracer, I know this value could change, but I want you to assume that it's not. And what we do then is we insert a guard. We turn this promote. The promote says, here's a value, and we want to assume that whatever value this value is right now is the value that it's most likely to be for the foreseeable future. And now jump to this block. So we resolve that information, and we say guard value with the value that it is right now, and then the block to jump to jump to if it's not true. And we'll see how this helps us in just a second. Okay, so for this really to look good and to make a little more sense, we have to do a little bit more complex of code. So what we're going to do is we have a program here, and we're going to enter right here. And we say promote X, and then jump to B2. Whatever X is right now, we're going to assume that's what it is, and for the foreseeable future, and then we're going to jump to B2. And then we do some calculations. We multiply 2 to, multiply X by 2, we set X3 to X2 plus 1, and then we subtract from I X3, and then we jump to L, which is another block up here, and we do a check, and then we'll do this loop a whole bunch of times, and after a while, when let's see here, when I is not greater than or equal to 0, then we go to done and print out the value. So we got a couple of comparisons here, some calculations, and yes, this is completely contrived, but the output demonstrates what we're going for here. All right, so if we execute this, here is our output. So what we see is right here, this is the trace. So if we go back up into the code here, when the trace is done, we do this assert trace. And what assert trace does is generate a new block with the trace code that we've created and swaps it into the known blocks. And we're going to actually want to print this out. So the trace returns this. There we go. All right. So when we executed this trace, we came back. Okay, we need to kick into the interpreter now at this block here, trace whatever number here, and here's the environment that we were at that point, which is kind of useless for this point. But here's the trace that we got out. And the trace is guard the value of X to 5 and jump to B2. Okay? And then we're going to do our multiplication, our add, our subtraction, and the greater than or equal to, and then guard true again, and loop. What does this mean? Well, if we look here, the greater than is actually from this block, and the if here that goes to L done has been turned into guard true, and promote has been replaced by guard value. Now, if you remember in the last part, we talked about partial evaluation. The next thing we want to do, and we're not going to do it today, but the next thing we can do is run that partial evaluator over this trace. And whenever we see a guard value, we can turn this value into a constant. So X is not a constant, it is a guarded value. So it says, if we get to this point in the code and X is no longer 5, then go to B2. And B2 kicks us back into the normal bytecode that we would normally execute, and we go into the slow path. Then, if we know the value of X, we can constant fold this instruction and this one until we get to here. So if this is 5, then X2 is going to be 10, and then this is going to be 11. So we can say we want to take I and subtract 11 from I. So this instruction and this instruction would get completely removed, and this becomes a subtraction, a greater than, a guard, and a loop. Subtraction, greater than, guard, and loop. And it just keeps going over and over and over again. Because we know X never changes in this entire code, never gets assigned, once we get into this trace, we could remove the guard. We could put the guard in a different block. So we guard once, then jump into the loop and just run forever. And then X2 and X3 are never used at all, so those are also removed. And we can see how this would collapse down very neatly. Once I reaches is no longer greater than or equal to 0, we have this guard true will fail. C is no longer true, C is false, and we go to L done, print and stop I, and we're done. And so that kind of bombs out of the JIT into the slow path. So this is very helpful in situations, like I said, where we say, this thing may never change, but it could. So for instance, what we could do in this example is we could say something like in the way PyPy, and there's a JIT for Ruby built on PyPy called Topaz. What these sort of systems do is that every time you change the class, so if you want to add metadata or add some data to the integer class or something, or you create a class called foo and you want to change the name of foo somehow, every time you do that, it increments an integer. That's like a revision number. So whenever you use that class, it's going to emit a guard that says, just assert at the beginning of all this code that this that the class revision number is this. And if it's not, then we're going to jump out of the trace and do something else. All right, so that's pretty much all we have for today. It wasn't too long of a video, but I'm going to try to make these videos line up very closely with the different parts of the blog series on JITs that the PyPy developers produced. But as you can see, all we really need to do now is hook our interpreter up to the JIT. So we could create a trace, and then we interpret the trace, and then we jump back out again and continue on. In fact, I bet we could hack that in right now. We'll have one problem with this, and that is we don't know how to promote in the trace, but in the interpreter, but that's very easily fixed. Trace start block is this, and then we can do interp. Our starting block is trace start block, and the instruction pointer is 0, and our environment, actually we're going to do this, keys, so this returns a map, and our keys are block and end, so this is going to be block, 0, and end, block, 0, and end. Alright, let's see what happens when we do this. That was not expected. Because we can't we need to actually hand it the block itself. Get blocks. There we go. And that's no difference at all. All right. Symbol. Well, I'm not exactly sure what's up there. Let's see here. So let's see. So we do where's our stack trace coming from? We actually have a problem with this is from the closure compiler itself. That's interesting. In our analyze. Let's make sure our interpreter is working here. All right, there's that, and no, same thing. Cannot be cast to symbol. At 233. Hash map cannot be cast to symbol. Oh, haha, that's interesting. I had this in a binding. Alrighty. I misread that as a let. Sorry for the delay, everyone. Let's try this again. Everyone right now is probably saying, yes, yes, we saw that 20 minutes ago. And then we'll remove the interpreter. Okay, so now if we run this, it says no matching clause for guard value. Well, that's easy enough to do. What we'll simply do is go up to our interpreter here and say, that's our partial evaluator. Okay, how about the interpreter? Here we go. So, guard value x, like sim, val, and block. And what this will do is say let resolved symbol be resolve sim and environment. And then if equals rsim and the value, then we're going to recur block inc the IP with the environment. Otherwise, what we're going to do is we're going to jump to the new block location, which is actually going to be recur get blocks, and then we're going to do block from that, and 0 and environment. Just so you know, I don't normally use dynamic variables this much. This is really kind of a nasty hack of just kind of hacking around and playing with this stuff, so it's not necessarily supposed to be beautiful. Doing a lot of dynamic variables like this is normally a really bad idea. And then we have a guard true, so we need to do the same thing, which is pretty much the same. Except here, we're going to resolve sim again. But in this case, we're just going to say, we don't need to do this, rsim. We can just say, hey, if it's true, then we continue on. And, oh, there's no value. That's why the pattern match failed. So it's not exactly the same. It's pretty much the same. There we go. And we need loop. Loop is also very simple. Loop. And this is going to be recur block 0 env. So we're just going to jump to the start of the block and continue executing again. And let's do that again. All right. Looks like it worked. So we see here I is counting down each time by a certain amount. Looks like it's pretty much exactly 11 every time, so that works. And we have our values here. So there we go. So in the next steps, what we're going to be doing is maybe looking a little bit into optimization. I think that's coming up. But the big thing that we're going to do next is to hook up the interpreter and the tracer together so that they go back and forth. This sort of thing here shouldn't need to be done. It does right now with the current state of our code, where we do trace and terp. But what we really want to do is to swap in between those. So the interpreter is constantly just analyzing the code as it's running it. As it recognizes patterns, it kicks into the trace mode. Once the trace is done, it kicks back into the interpreter mode, and we can just run on and on. So there you go. I'm going to upload this code to the same place as I had it before. Have fun taking a look at it. Click the like button if you enjoy these videos, and thanks once again for watching.